Hey guys, this video is going to cover the 3.5 notes, which you should print off from Canvas if you haven't already, and then follow along with me here. What we're going to be doing in this lesson is finding real roots of polynomial equations. Our objectives: identify the real roots of polynomials by factoring. We're going to also identify the multiplicity of real roots and what it means for the graph of a function, and then use the rational root theorem to solve polynomials. Okay, so first of all, we've already talked about zeros, but I just want to make sure that you're understanding what they really are. This is important. It doesn't say this in your notes, so you need to add that. The real zeros of a function, of a polynomial function, are the x-intercepts on the graph of a polynomial function. They're also called roots and solutions. Alright, so I want to show you a couple of graphs here. So in the first graph, it looks like we have the red graph here, it looks like a parabola, which is a quadratic function, x squared. In this particular graph, we see that there are two zeros, two x-intercepts. So if you think about what the y-coordinate would be, here's your x-axis and your y-axis. Your y-coordinate, when you're on the x-axis, is 0, so that's why they're called zeros. But now, we can have this next graph right here has 3 zeros. And those are all real zeros because they are x-intercepts. And then this third graph here has 4 zeros. Now, I can move the graphs around here. Let's say that you have a parabola that actually just hits the graph, the x-axis, in one point. Well, what that means is we just have 1 0. So you can have a parabola that has just 1 0. You can have a parabola that had 2 zeros, like our last example. Or you can have a parabola, maybe it's not even ever intersecting the x-axis. You have no x-intercepts, but you would still actually have zeros, and those zeros would not be real zeros, they're going to be complex. If it doesn't intersect the x-axis, and let's say this is a polynomial of degree 2, it's going to have exactly 2 zeros, but sometimes they might be real zeros, sometimes they might be imaginary. And if they're imaginary, it deals with the square root of -1. Oops. And that's when it doesn't ever cross the x-axis. This next function I can move, so right now there are 3 zeros, but let me get rid of those here. We can also have a graph like this that has 2 zeros. So I've got I have 1 0 here, and I have another one here. And the fact that this one crosses through the x-axis, and this one is just touching it, which is called tangent, when it comes towards the x-axis and then it goes back in the same direction, it goes back up instead of crossing through. That's called tangent to the x-axis, and we're going to talk about when that happens. What types of zeros make a graph tangent like this? So we had, at first we had, with the green graph, we had 3 zeros. Now we see a situation where you can have 2 zeros, and if I move it, I can move it down like this. Now I only have 1 0 right here. So when it's and you notice this has 2 twists and turns in it, meaning like a relative maximum and a relative minimum. We're going to also be talking about that. What does that imply for the graph? What kind of function is it? And we'll be getting to that later on. If you look at this last one here, currently there are 4 zeros. 1, 2, oops. We have 1, 2, 3, and 4. And I can shift this graph up. Remember, with our transformations, if you just add to the function, it'll shift it up. I could shift it up to like here, and then now I have, you guys identify the number of zeros here while you're waiting for me. Here's 1 0, 2 zeros, 3 zeros, so I might have 3 zeros. I could shift it up even further. Now I have just 2 zeros. this one and this one. I should clarify, two x-intercepts. And you're going to see later on that we actually still have 4 zeros. And two of the zeros will be imaginary zeros here in that situation. And I'm kind of jumping ahead here, but this purple graph could also just have 1 0 if it just hits the x-axis in one spot like that. Okay, back to our notes. Put me up there. Okay. The zero product property. What the zero product property says, and again, we've gone through this before, but it says that if you have two things multiplied together and you end up with it equaling 0, then, so it should say if a times b equals 0, then the zero product property says either then a equals 0 or b equals 0. So if either factor is 0, the whole outcome will become 0. And we're going to use that when we solve quadratics by factoring. We've done that with quadratics. I'm sorry, when we solve polynomials by factoring, you're going to use the zero product property, but we have used it previously in chapter 2 when we solve quadratics. So it should look familiar. Okay, so look at example 1a. We're going to solve this by factoring. So think about what I've said several times. When you are factoring, the first thing you really want to look for is there anything that you can factor out that's a common term to all of the terms. So you think about that. Common terms. So for this polynomial, before I even go a step further, when you're solving these polynomial equations, you want to make sure that one side is equal to 0. We're going to be finding the real zeros of polynomials, which means you need one side to equal 0. It already does for this problem, so I don't need to worry about it. But now, if you look at these numbers, you've got 3, 18, and 27. They're all divisible by 3. And then this first term has x to the 5th, x to the 4th, and then the third one has x to the 3rd. What's common to all three is 3x to the 3rd power. What's going to be left inside the parentheses, we pulled this 3 out, and we pulled 3 of the x's out. So x to the 5th, again, remember, means x times x times x times x times x 5 times. 5 times. We've already got 3 of them on the outside, so what's left inside is x squared. And if you think about it, when you distribute it back through, you should get what we started with. 3x cubed times x squared would give us 3x to the 5th. And then 3 times 6 gives us the 18, and we only pulled out x to the 3rd, so we still have one remaining x here. And then this last term is going to have 3 times 9 gives you 27, and the x cubed is pulled out, so I don't need that. Okay, now, and I know that this is equal to 0. Now I have this partially factored, but now I have a quadratic here inside the parentheses, and I want to continue factoring the quadratic. So different types of factoring, we talked about it in 3.4, factoring out common terms, which we just had to do. Now we have a quadratic here, which you're going to factor into two binomials. You try to factor it, pause the video, factor it, and see if you get it. So x and x, and then plus 3 and plus 3. So by the zero product property, which can be expanded, I have just two factors here, but if you had a times b times c equals 0, and you could keep going, you could have times another factor, then a equals 0, b equals 0, or c equals 0. So in this case, we have 3x cubed. So we have 3 times x cubed. 3 is never going to be equal to 0. So we're going to set x cubed equal to 0 and solve that. And then we have x plus 3, and we need to figure out where that equals 0. And then we have the same exact factor here, a repeated factor. So I don't need to solve that twice. I just need to solve it one time. And so solving x cubed, you take the cube root of both sides. The cube root of 0 is 0. So x equals 0 is one of my solutions, or we can call it a 0. And then here I'm going to subtract 3 from both sides, and I get x equals -3. This is my other 0 for that polynomial. And that is how you solve a polynomial equation by factoring. I'm going to stop there and we'll pick up with example 1b in the next video.